Today, we're pleased to welcome Brian Gunter. Brian's in the School of Aerospace Engineering, came to Georgia Tech in 2013, right? As an assistant professor and was promoted to associate professor in 2019. Selected as a BBISS faculty fellow in 2022. Prior to coming to Georgia Tech, you were at the Delft University of Technology in the Netherlands for 7 years, and then was postdoc at UT Austin prior to that. Got you're Texan by nature?
No, I just ended up spending a lot of time.
Spent a lot of time there. All right. So mechanical engineering from Rice.
Yeah.
MS PhD from UT Austin. Your research, I won't try to go into the full detail, but I understand that various aspects of spacecraft missions and their applications, many of which are directly related to sustainability and climate. And today you'll be presenting on new solar power architectures for Earth and space applications.
Thank you very much. Appreciate it. And the talk, at least based on some of the other talks that I've seen, this one may be a little bit more on the engineering and the technical side of things, but that's okay. It's good to mix things up. Like Michael said in the introduction, I work on a lot of different things. Anything for the most part space related. So this is just one of the elements that I wanted to focus on that was related to sustainability. There's other things that I do with regards to remote sensing and climate change and things like that. But that's for another day. So today we're going to focus on a topic that I have really been focusing on the last 3 or 4 years on space solar power. And you're going to hopefully get a better picture of what I mean by that, because this can mean a lot of things. And you're going to see some of the, not only just at a high level, what I'm talking about, some of the new initiatives that are happening in general in the industry, but also some of the very specific things that we're working on here at Georgia Tech and with some of my students. So it's always good to take the mile-high view and look at an overview of sort of what the expected power usage is in the future. And this I grabbed from just a reference paper that I look at a lot when it comes to space-based solar power. And you can see here that there's different projections. And of course, the higher the population, as you see, it goes from 2010 all the way out to 2100. There's going to be potentially significant increase in population, but you see a steady increase in the total energy usage. And we see this already, we rely on energy for more and more things. And so even going from, 2010 to 2030 is a doubling, and 2030 to, 2090, we'll see another doubling in terms of our energy use. So currently we're at 8 billion. So the projections seem to be, pretty good, at least in terms of population. And so the obvious question is, where are we going to get all this energy from? And many of you are probably much more knowledgeable than me on some of these other renewable and sustainable power generation technologies. There's wind, of course, solar, hydroelectric, geothermal, biomass. I'm not putting in fossil fuels in there because that's not renewable or sustainable. It is a energy source. And they keep teasing, at least as long as I can remember, nuclear fusion as being the clean energy of the future, but that still remains to be seen.
So it's 10 years away.
Microsoft thinks 5 years.
And these are all very good and viable solutions. Each of them have their own limitations, to include some of the things that I'm going to be talking about. I'm not trying to claim that what we're working on is also going to be the magic solution that fixes it all. I think all of these types of sources are going to be needed to meet our power demands. But they each have their limitations. For example, solar, at least when we think about it in the traditional sense, and I have a slide on that next, is typically certainly intermittent. You're generating power during the day. Maybe wind is intermittent, depending on weather systems and all that sort of thing. And of course, they all have some level of environmental impact, whether it's a dam that's maybe blocking a river and a river basin system in the ecology, or solar and wind taking up lots of space and real estate, and the resources to build the the collecting technologies. So typically, I assume that when most people think of solar power, for large scale solar power generation, not just maybe panels that are on your house, on the roof of your home, they're thinking of these large solar farms where you have large tracts of land, and this is just an example that I grabbed for a 180 megawatt farm that's out in Texas. So this is the traditional sort of terrestrial solar farm that we think of for solar. But one of the notions that we've been exploring is thinking about moving these solar farms on orbit to space. And there are a lot of benefits to that. One is if you put it in the right orbit, those panels can be pointing at the sun 24/7 all the time. Like there's no intermittence. You can be generating just a tremendous amount of energy unobstructed by atmosphere, by anything else, 24 hours a day, 7 days a week. And so that's a huge positive. Of course, the downside is it's great that you're generating power 24/7, but how do you get it down, right? That's the $1 million question. How do you get it from these colossal things that may be orbiting and get it down to a usable form on Earth?
Is this sort of like Leo, Meo, Geo?
It can be any of them,
Okay.
and we explore all of them. But if you're talking about these super large structures, and this is not a new concept. They've been thinking about this since the '60s at least. Where you see here, these are giant kilometer scale things with thousands of different solar collectors. Here's an example of a concept in the '70s that was a giant sort of space elevator. These things would be wired to the Earth, and these massive structures. The one on the right is just sort of like a collector focusing, they call clamshell infrastructure. So they can be Leo, they can be Geo, like very high. The higher they are, then of course the less disruption they have on satellites and other things that might be in the lower orbits.
For our non-aerospace audience, Leo, low Earth orbit.
So low Earth orbit is traditionally what you might about the orbit of the space station. So anywhere from 400 to about 1,000 kilometers. That's where all of the Starlink satellites are. It's where all of the communications, or at least the low Earth or the fast moving ones are. And as you get higher and higher, you get out to what's known as the geostationary orbit, where the orbit is the same period as the Earth. So it's always over the same spot on the Earth because it's orbiting at the same rotation rate of the Earth. That's a very high orbit. That's about 36,000 kilometers, if I'm not mistaken, in altitude. So those are much higher. So we're talking 400 all the way up to 36,000. But of course, that's further, you have to transmit your power. And that's also a lot of the trade-off. It's a lot easier to launch something only 400 kilometers away as opposed to 36,000. But at the same time, it's moving faster over the Earth. It's not stationary over the same point. So there's a lot of trade-offs. And I'm not going to get too much into that element of it. That is definitely something that my students and as aerospace engineers and orbital mechanics people, we love to look into. And there are some nice trade-offs on all that, and we'll talk a little bit about. I'll give you a flavor of it, but we won't get into too much detail on that. So anyway, I just wanted to say, this space solar power concept isn't new. We would love to do it, but that hard part is generating enough and getting it all down. So John Mankins was sort of one of the large pioneers. He was an engineer at NASA for many years. He's since retired, I believe, although I think he's still active. And he was a real champion for this large scale solar power systems in space. And this was some of the concepts that he had. And you can see here, we'll talk later about what should you do? How should you beam this power down? So while these ideas have been around for, in some cases, decades, they haven't been very viable. But things are different now. Our access to space, in particular, has gone up tremendously. So and thanks in large part to companies like SpaceX and Rocket Lab and many other launch providers who are now were able to offer very quick, high frequency launches for for lower cost than it has ever been. And it's all run by a private company, so there's not necessarily as much government, so like NASA safety restrictions in place. So things can go much, much faster if it's going at a private industry pace. And you can see here, if you've not seen this, in the middle panel on the right is one of the stacks of the Starlinks. So when they launch 60 or 100 of these Starlink satellites per launch, they literally stack them up like pancakes. You can see it can be very efficient, and they reuse these rocket bodies. So they've really driven the cost down, and they've accelerated the ability for people to access space and put things on orbit. At the same time, lots of technology is being matured. So just even from a university perspective, we've been miniaturizing and doing technology demonstrations at the university level with our small sats and our CubeSats, also since the 90s. So we're getting better and better about controlling, making sure these small systems can operate. And the lower mass you can make, the more capable technologies you can have, the more you can do. And so we're getting there with that. To include, these large systems, and we'll talk a little bit about this, you're not going to manually assemble these things. You're not going to have an astronaut up there that's flying around and it's assembling these thousands and thousands of components. They're going to have to be built essentially using robotics or some sort of autonomy. And so there's been a lot of research. That's also a very growing research topic in the last couple of decades. In addition to just the power transmission technologies themselves, it's one thing to say, oh, I want to beam power down. It's another thing to actually make the technology and demonstrate it and improve upon it. So those have all made some nice advancements. And in addition, I'll talk about this because we're involved in some of these, there's been some really nice federal funding initiatives to promote this very concept. So before we get into some of the technical details and some of the things that we're actually involved with here at Georgia Tech, it's useful to also just explore a little bit about what would be the benefit of this. What is the return on investment for these types of systems? For this, I'm going to turn to a presentation that was actually led by another PhD student of mine, Miles Turner. So he was working also on this solar power satellite builder concept. How would you build these large structures? What would be their efficiencies? What's their carbon, their CO2 offset? What is the real benefit of this? And can we demonstrate that if you build these things, that there will be a long-term, overall offset, generating enough power that you're not burning more resources than you're actually thinking you are going to recover. So he presented this a couple of years ago and won an International Space Solar Power Student Competition as part of that. So many of these slides were from him, so give him credit on that one. And so what Miles was looking into was some of these large space structures and how we go about building them, what would the mechanisms be, how would we construct them. I've already mentioned that we want to have these things built semi-autonomously. And mainly, we're looking for these things to be, you launch these things in small packages, they self-assemble to be very large structures, and then that creates, you can leverage some of these SpaceX Rocket Lab launch capabilities and get many, many launches with small payloads, but then build large structures. And so here's the overall concept. It's fairly straightforward. You have in this case, we were exploring a very specific modular type of solar structure concept that was built from these components that would attach together through electromagnets. That saved a lot of effort. They could, you can imagine a series of magnets that were, if they're electromagnets, they can activate when they need, they can repel, they can attract. You avoid some of the issues and some of the complexities of having to individually maneuver some of these things if you can leverage those systems. And there's other folks at NASA that are demonstrating that technology even now. So we borrowed that concept as an initial idea for what these individual modules would look like. And then we said, all right, we could leverage these, perhaps using ride shares for non-aerospace engineers. A lot of times when they launch any rocket, there's extra mass, there's extra space on them. And they will sometimes make that available, sometimes free, sometimes at a discounted rate. And if you design your spacecraft in the right way, you can fill the little nooks and crannies that are remaining on some of these launch vehicles, and that's called a ride share. So you can get your satellite to space, sometimes for a very inexpensive cost. And so the notion is if we leverage things like ride shares, even dedicated launches, we can spread out some of those costs over time, and we can build this system over time. And so our notional design for something like this, because we wanted to actually construct a large system, price it, use some of the systems analysis that we have and the cost models that we have to assign not only a dollar value to what it would cost to build the spacecraft, but then also think about how many of these would we need, what would be the launch cost, what would be the overall cost for the large space system, but then also balance that with how much energy is it generating, what are the efficiencies, and so on. We'll get to that. So this is our nominal design of, a 1.5 meter by 0.5 meter individual unit, and each one of those would expand out so that you would get this sort of 1.5 meter by 1.5 meter solar panel at the end of it. And I won't get into the details of the mechanisms that kept everything together, but you could think of these as maybe just a series of connecting modules that would easily go together if they're in orbit next to each other. So they're interchangeable. So the nice thing about that is if one of them fails or gets hit by debris, it could be replaced, and the whole system as a whole can be maintained long-term. So it's not just a one-off, one-use, use of resources, and then it all deorbits and burns up in the atmosphere. That's very wasteful. It's something that could conceivably be maintained long-term. So when you put all this together and you talk about the cost, at least in current dollars, what it would take to machine, and we have a good idea. We launch in my group, build and develop and launch small sats. We've launched a number of them, so we have a good idea what these units cost. They are approximately, for each one of those, for about a 200 kilogram satellite, which is right on the verge of what is called a small satellite, about $250K per satellite. That's for all the testing and the hardware and attitude control and all that. And so we chose this electromagnetic capability for a lot of reduction in terms of vision sensors or other types of thrusters that you might need for docking. This was just sort of an efficiency. We haven't demonstrated this in a hardware prototype yet, but we're working on that. But the nice thing is that when you have the coupling and they're locked together, then you sort of build in the energy transfers, and allows you to build these really large structures for that, and they're easy to manufacture and all of that. This is the notional concept, the concept of operations. We do this a lot in aerospace engineering. We have CONOPS for a mission. You would start with one launch. It would have multiple different components, what we're calling builders. They would self-assemble. So you would have one section of it, then that would remain in orbit until the next launch comes up. It would build it would attach, and so on and so forth. And you could build these of really arbitrary size, which is great because they're scalable, repairable, and all of that. This is a nice animation that shows, thinking of the Starlink image that I showed a few minutes ago, where these things are just stacked up. If you released all of these, this is just, and these were some of the algorithms that Miles was working on to specifically break those up into a tall stack into there's 3x3 panels that I was just showing you. And we won't go beyond this. I just wanted a short animation to show you that this is what it looks like. It's also, I think, useful for people who are not used to looking at things, at orbit speeds, just how fast they're moving relative to the ground. And if you think about transmitting this power as it's zipping by at 7.5 kilometers per second, especially when you're in low Earth orbit, you're only going to be gathering a little bit of that data at a time on the ground. So that's why there's some appeal to going higher, so that there's not as much pass, or you don't need to have long collection fields and things like that. So the case study that we looked at, this one is in low Earth orbit, was we nominally said, let's have 1,000 square meter size panel. And so for that, because each of them were 1.5 meters by 1.5 meters, and we counted for a little bit of losses in there due to gaps and spacing and things like that. In general, you're going to need 450 of these, just as a nominal case, like 1,000 square meters. You know, that's it's a fairly good size, but it's not as big as some of these early concepts would be. So it's not too unreasonable. The idea was all of these will be built just on those concepts that we just showed. And you could move this to MEO, which is a little bit higher orbit, I think more like 10,000 to 20,000 kilometers. And there's highly eccentric orbit, which has some nice efficiencies, but then we're getting into, you know, really lots of orbit analysis and things like that. But these could be deployed really anywhere. So this is sort of what it would look like when it was fully assembled. We targeted, in this case, a 1,500 kilometer orbit. And we said we could do that for 4 launches. We stacked 115 of these together. That's not unreasonable given what especially Starlink is doing. They're launching thousands now and have plans for tens of thousands in the coming decade of satellites. So very possible. And the analysis, and I would encourage everyone, if they're interested, to see how we did this, computed a CO2 carbon footprint for this, both the spacecraft and the launch and all of that. We used some metrics that we got from the Department of Energy that basically associated a total carbon mass to maybe a kilowatt hour of energy produced. And we used that to essentially leverage that the energy that it would cost for the launch, plus building the satellites and all of that, was about 1,600 metric tons for such a system. The individual launches, so this is, you know, you can go onto the SpaceX website right now, and if you have $62 million, you can buy a rocket launch. This is the nominal price for that, not accounting for free ride shares and things. So we tallied it all up. Oops. And you need 4 of these, and all of them cost 115 million. So, you know, your whole cost for building one of these things is $363 million. This is using 2021 data. There could certainly be some economy of scale if you're building these really at large volumes and you're dedicating this. But, you know, to be honest, this sounds like a lot of money, but $300 million for a dedicated NASA launch or any other launch is actually on par. It's expensive to do all that stuff. And we're talking 4 separate launches. So we'll get into some of the technical details. You know, we were looking at different types of solar cells. There's different materials you can use that have different efficiencies. You know, some are better than others, so silicon and gallium arsenide, but there may be some cost benefits and mass benefits and things like that. Carbon offsets are different depending on whether you're using silicon or gallium arsenide. But so gallium arsenide maybe has better efficiency, but it has and as a result, it gives you a little bit better carbon offset. So the energy that it's using is more efficient. And so when you get up on orbit, you're getting 1,380 watts per meter squared. That's the energy that's coming from the sun that's at the top of the atmosphere. And so here's this amount that we grabbed from a DOE research report, where the amount of CO2 per kilowatt hour at least generated on the Earth for most terrestrial applications was 0.417 kilograms per kilowatt hours. And that was our number that we were saying, look, if we can do better than that, or if we can start offsetting so many kilograms per hour with our space-based system, then we're hopefully gaining an advantage over doing this terrestrially. And if you, without getting into the details, these are the list of efficiencies in terms of, you know, when you start converting things from sunlight down to the microwave transmission. I have another slide that's a little bit more descriptive on all this. You know, you're losing efficiencies at each stage, and so ultimately, what actually gets down to the ground is just a small fraction of what is actually on orbit. Of course, they're trying to work on that better and improve that. But here's the summary chart. So here's kind of the takeaway from a lot of this stuff, because it says, okay, for one of these systems, this 1,000 square meter surface SPS system, it's in 1 hour, one system is going to generate, depending on whether you're using silicon or gallium arsenide. I'm going to stick to the gallium arsenide because that's just a more efficient material. So in 1 hour, one of these 1,000 square meter SPS systems is going to generate definitely enough to power a US home for a day. If you keep going, and let's say you were to have multiples of these on orbit, you can see in 1 hour, if you had 4 of them, it could power a home for a month. It could power the Sydney Opera House. I don't know why Miles chose specifically the Sydney Opera House for that, but maybe it's a high energy user. Point being that in 1 hour, you could conceivably generate with multiple systems a significant amount of power, like 2,000 plus kilowatt hours. And when we look at in terms of carbon offset, certainly when we go from one of these systems to 2 to 3 to 4 to higher numbers, it gets better, of course. But we're offsetting also more and more carbon because we're being more efficient in our power generation on orbit than we are on the Earth. And so at some point, we become we're generating the offsetting let's say, for example, with 9 or 10 of these systems, or one system just running longer offsets like a 1 megawatt natural gas power plant per day. And I don't think I showed this, but basically to make even these systems carbon neutral, like the net carbon offset from all the costs of building, designing, launching these, and their carbon offset while they're operating very efficiently. I don't think I showed this, but in the paper, it basically comes down to you need these systems to run anywhere from 4 to 9 years, depending on the solar panel material. But the average lifetime of the solar panels is 20 years or more. And so we essentially have made the case that these systems, if they have the efficiencies that we're showing, are more efficient, but they need a long run time to make them valuable, like 5 to 10 years.
That 20-year lifespan is in space?
Yes. So that's the the average beneficial lifetime of these solar cells of either the silicon or gallium arsenide, all of it.
So I had an official question. So I was trying to glean from the previous simulation. So is it a large sort of air gap in between the panel that's closest to the Earth and I guess the surface level? Or
It depends. Think of this giant 1,000 square meter panel just facing the sun the whole time. So in space, there's you're not really worried too much about. There is drag, but it's very slight, and you can maintain an orientation with respect to the sun on that one. So that's also the assumption that this thing is pointing at the sun continuously, during the hour that we're doing the numbers. Does that make sense?
So I was going to ask, would that be ionizing radiation, like that radiation that's coming from the solar panel and coming down to the surface? Like, is that?
Oh, we'll talk about how they do that because there are different ways you can do that. That's coming on a future slide. There's different ways you can get the solar power. You convert that energy, all those photons that are coming from the sun, and you convert that into energy in different ways and beam it down to the Earth. But we'll talk about that.
Are you also just going to compare this to sort of terrestrial solar?
We have not done that because of the same solar cells, by and large.
Okay, it's just it doesn't cost 360 million to deploy an array.
That is true, and we do get into some of the cost benefits on that.
Okay.
It would be an interesting study to see what would, for example, that solar farm that I showed. What's the cost of that versus what's the cost of putting it on orbit, and what's the longevity there? You don't have any atmosphere or weathering or any of those systems like you would on a solar farm, but it's probably not $300 million either. So there is some interesting studies that
is there, because I feel like that's
cost benefit. Yeah,
that's how the policymaker is going to be sort of evaluating this, right? Like rather than break even on this project, it's relative to what else.
And also we're counting on, we made a lot of assumptions and we haven't taken into account these economies of scale and things like that. And so that is definitely an interesting thing that we would love to explore more. We did it partially in the paper, but more to be done there. We definitely didn't answer that question. So,
Ryan, I have a couple of questions.
Sure.
This is Daryl. Just curious, as a maybe side curiosity item, how much of an emission load happens getting these things off the ground and into orbit relative to their
It's
lifetime?
true. And we wanted to account for that. The way that we accounted that is we looked at the carbon footprint of them. And we
Right.
said that there would be 400 metric tons per launch for these things. So we were trying to account for the some effect of it. Now there are definitely arguments to be made about what else is it doing to the atmosphere? What else is it doing environmentally besides just carbon offset? But
Right. And
Yeah,
what
I
is
would
the
have to look into
contribution to space debris to the extent that that is a problem? Is it a problem, or is that just a popular press thing?
It could be,
Space
and
debris is a
this is
problem.
also where, well, I touch on it a little bit because I do work a lot in orbital debris as well. The systems in LEO, at least with the materials and everything that we make them from, like this nominal spacecraft, this would re-enter, so it wouldn't linger on orbit, and it would fully burn up. The problem is when you go all the way out to GEO, these really high orbit satellites, it's very difficult to get something that's very, very large back to Earth again. So what they end up doing is pushing it out to an even higher orbit just to get it out of the way. But that's not a very sustainable practice of just putting, continuing to put debris out in these graveyard orbits, what they call them, over and over again. And so it's something that would love to find a solution for, and it basically just means you have to have active deorbit systems, that everything you put up, you have to have a mechanism that can bring it back down again. So it can be a debris problem, especially if you're talking, and this is an issue that we're dealing with also as we look at Starlinks and CalPERS, and there's 100,000 satellites being proposed to be launched in the next decade. How do we ensure that all that stuff is going to come back down again? So in general, the aerospace community and policymakers are very concerned about that, but I think it's a solvable problem, although there's not definite policies and solutions in place for it now.
Right. I'm curious, so I don't know if you've heard of Project Drawdown that had tried to calculate, there's these 100 solutions to reducing carbon emissions, and looking at if you could do this at scale, what is the cost and what is the feasibility, et cetera, et cetera. I'm pretty sure that this solution is not in there. So that's an offline item, but I'd be curious to see how at scale, how it compares to like refrigeration, for example. If you can solve the refrigeration problem, which is a very difficult distributed problem, not a point solution, that's a top 5 according to their calculations. It's interesting to think about where this falls in that context.
Yeah, no, that's interesting.
I'll share the
drawdown. Yeah, share that with me, please. So the main point was, we're starting to look at not just the engineering, not just the technical side of it, but we really want to make a solution that we think in the long term is beneficial, more beneficial than not having it. So at least that's the goal. And of course, a lot of future work going on with this, and we're dealing with a lot of it in terms of what trajectories, where do you put these things, how many systems, looking at debris and the other technologies that would allow us to build all these structures and things like that, and trying to find some nice optimizations on that. And that's where Miles and Dario and others are looking to explore. So this, I think, maybe answers your question that you had. We've only talked about these magic systems that get on orbit. How do we actually get the energy down? Like, what are the mechanisms for that? And and as a generalization, you have basically a couple of options. You can either use optical, think lasers. So you're concentrating, and lasers are very efficient because you can concentrate that energy into narrow beams. So that's efficient. But you run into lots of issues with clouds. You're not transmitting. There's lots of diffraction. Of course, on a cloudy day, you're not getting anything. So then the alternative, which this table summarizes all the kind of the plus and minuses, the pros and cons of each system. You can get into radio frequencies, so millimeter waves and microwaves systems that, of course, go through clouds. So these microwave systems aren't necessarily disrupted by cloud cover and rain and all these other things. However, they have other things about them that aren't so good. You need these really large aperture sizes and transmit and receive antenna sizes. So you need large ground antennas and large transmitting antennas. So the structures tend to be larger. The other thing about optical, even though from an energy conversion process, it's maybe a little bit more efficient, but you can't zap high-powered lasers from space because you have to worry about eye safety, right? You don't want people actually getting eye damage looking up and getting, you know, some sort of laser transmission. So there is eye safety that they are concerned about. And this is another figure. Both of these are taken from this paper from Rodenbeck that I think is also really useful. It also shows at each one of these steps, yes, you're getting the incident solar cell, you know, that's your 1,000 megawatts. Say this is, you're getting 1,000 megawatts of energy. The cell itself has some efficiencies that it's going to lose. It's not going to convert that perfectly. So maybe you get 650 megawatts out of that. And then there's some various, and this is mainly on the electrical engineering side of things, these conversions, as you convert it to DC, and let's say you want to convert it to a microwave or millimeter wave radio signal, RF signal. There's some, each one of these steps has these efficiencies, has to go through the atmosphere. You have to collect it. There has to be a rectenna that converts it back from RF to usable DC power again. And so at the end of the day, you start with 1,000, and really what's delivered is just about 13% of that. So about 130 megawatts of that as a number.
So I guess just two questions. Number one is what frequency were you all looking at, like transmitting all this in? And another question is, I know one of the biggest problems with wireless power transfer is the idea of ionizing radiation and like things heating up that's in the like line of sight between the transmitter and receiver. So I guess like what's your sort of idea about keeping it safe so that, I don't know, birds aren't getting vaporized or something?
Yeah, I think the systems that are being demonstrated are certainly taking that into account, because you can't have really concentrated. I mean, any of the concentrated energies can, I think, be damaging if it's if you're not careful with it. But my understanding is that the RF that is being transmitted for these proposed systems are not at the safety hazard that I'm aware of. They're not directed energy at that level where they could almost cause skin damage or anything like that, that I'm aware of. So it is an interesting question, though. If you have this really huge system on orbit, it depends on how concentrated you make it, because radio signals themselves have this dispersion about them. So it depends on how concentrated you make it, probably. But as far as I know, lasers much more the concern on that one, because that's a very efficient concentration of energy of light and photons. RF is more spread out, so not aware that it's an issue. Are you thinking, especially over hundreds of kilometers, maybe thousands of kilometers, the signals get very, very big. It's a 1/r² dilution of the power, just because it's going from space. So maybe, I'm not sure if the ones that the instances you're talking about are those for like airplane to ground, or even like the recharging units for your phone and things like that. Do you have, do you recall specific examples for that?
I know back when I was in industry, I worked at Intel and I was trying to do stuff with wireless power transfer, and there's a whole bunch of legislation on actually non-ionizing, but non-ionizing is what like heats people up, it heats things up. Whereas like ionizing will strip, you know, H-bonds and stuff off the DNA. But anyway, I mean, it's all really interesting. So if it's that dispersed, I'm just curious, like, how do you even get it accurately targeted towards whatever's in?
Well, that's one of the benefits of using RF, that you don't need to, because you're getting that same sort of power transfer per square unit over big areas. So now the downside is if you want to get all of it, you need large collection panels. But if you only have limited collection panels, you get whatever that power per square meter is. Oh, and just for reference too, I don't know if I have a full slide on this, but the frequencies that we're looking at for microwave is about 10 gigahertz. So it's, at least that's the common frequency that I've been working with for some of the systems that we're dealing with.
So probably no interference with the ISM band. And
So it's X-band, signals. And here's ultimately what, you'll see a system that, we're working with, has, it's getting the incident light coming from the sun. You have these, photovoltaic cells, your solar cells. And then there's some circuitry in between that converts that, into some sort of microwave or X-band or something like that. And then it's an antenna that actually transmits, that energy in a directed fashion. So one of the exciting developments I sort of teased at the start, that there were some new initiatives that are taking place. One of them is called the Space Solar Power Incremental Demonstrations and Research Project. It's a mouthful, which is why they have the SPIDER acronym. And it's an initiative sponsored by the federal government, specifically the Air Force Research Lab, their Space Vehicles Directorate, to really focus on getting space-based solar power collection and transmission capabilities demonstrated. And they have three main initiatives that they're talking about: Arachne, Spindle, and Spiral. I'll show you a graphic on that next. But this is sort of the longer term vision of it, where Arachne is the first of the demonstrations. And you'll see more about this because we have a nice experiment going on with it. But it's, these are all phase 1 experiments. This one is actually going to demonstrate that conversion, that RF power beaming, the X-band power beaming experiment from space to ground. I believe the Spiral is the collection point on the ground, and Spindle is a large sort of flexible structure. Think of like a big flat sail that could also serve as an on-orbit collection point for some of this power as well. But these are all small, so these are all 10 meter squared size systems. And the vision, of course, is to go into 100 meter, 1,000 meters. So this is the one we were exploring, to possibly even larger. And the whole notion is to try to, explore this technology, develop it, and see, does it actually work in practice, and does it deliver the energy or the benefits that we think it does. And so what's our role in all of this? It turns out, were selected. We proposed, submitted a proposal to the University Nanosatellite Program, and they were offering for this was the first time they've ever done it, this thing called the Technology Insertion 1. Typically a UNP project is you're starting just a small satellite from scratch, and the team doesn't have a lot of experience, and it's mainly a training to get student teams familiar with space systems. This one was very targeted. It said, we want a very specific mission for the SPIDER program. And there were some constraints for it, and it all had to do with this SPIDER program. So we proposed it, we were selected. The mission that we proposed was called WEBS, the Wireless Energy from Beam Signals mission, trying to stick with the SPIDER Arachne theme, of course. And so it's myself and Professor Greg Durgan over at ECE. We are managing this mission, and its goal is going to be to build a 6U CubeSat. So 6U CubeSat is about the size of a shoebox, not big, but it is going to be receiving this RF beam signals from this Arachne spacecraft. So you see here on the left, this is the Arachne. So that's being developed by AFRL. And our CubeSat, you'll see here, and some call-outs in a second, will be in one of these little deployment boxes. So they're basically just going to shoot us away and start beaming power at us. So we are going to be, hopefully, the first on-orbit demonstration of solar power beaming. So we're pretty excited to be a part of that. This is the CubeSat right here. We'll get into a little bit more detail. I'm an engineer, so I like talking about that stuff. And we're delivering this next year for ideally a 2025 launch. So we'll know in just a couple of years, hopefully get some first on-orbit data from this technology. So this is the conceptual operations. It's, to be honest, the entire mission itself is only, the nominal mission phase is only, I think, 5 hours in duration. Arachne is just basically going to kick us out, and we are going to tumble on all different types of orientations and gather information on our relative position, the total voltages that we're collecting from the power, and our orientation. So position, orientation, and power is our primary goal. Because as we're tumbling around, they want to see what is the power generation from these receiving antenna panels, and is it matching with what they thought? And if we go past this first 5 hours and they want to do additional experiments, they certainly can. But we're gathering up all this data. We're beaming it up to different sources. We're using the Iridium constellation, beaming it up, and we also have some S-band ground stations that will be beaming data down on. Here's just a quick look at the structure itself. You'll see here that these large sort of salmon colored panels, those are the antennas. Those are the things that are actually going to receive this 10 gigahertz beamed signal and convert it into DC power. And all the other instrumentation, there's GPS receivers on there. There's our own solar panels because we have to power our systems as well. We're definitely not getting enough power from this. This is just a demonstration, so we're not using any, and it wouldn't be giving us enough power anyway to run our own satellite. That would have been cool, but that's not how it is. And there's lots of other just systems that are involved in this. I won't get into the details. There's imagers, there's other things.
How doesn't your box maintain orientation to why is it tumbling?
They want it to tumble, which is why they want us to put these rectennas on all different sides, because they want to see how the power is received at different orientation angles. So just to have a tumbling spacecraft, and as long as we know, so we know what the orientation of our spacecraft will be down to less than a degree, really a fraction of a degree. So, and we'll know how far we are from Arachne down to a meter. And that's all the information they want to know to validate the technology. So, yep, the main thing that's doing all the work are those rectennas. You pop the top off, and here's all the insides of it, all the avionics and imagers and magnetometers. These are all the things that we use we do have magnetorquers that allow us to do some attitude control, but we're basically we're using those not to do controlled pointing, but to slow the roll. We don't want to have it go too fast. Here's all the actual hardware. We've got all the electronics, and this is stuff that we develop in our labs. And again, we're getting pretty close we have full flat sat. So this is all the satellite components all laid out flat. We're getting very close to assembling everything together into the flight units and starting the final flight test. We'll probably deliver this early in spring of next year. Here's the actual physical rectennas themselves. These you can read all about it. There was a paper in 2021 from our colleague, Brian Tierney at NRL, who is developed all this. So NRL was responsible for developing all the rectennas and power. And there's a really comprehensive paper here if you want to learn all about it and how they're designed and how they do it. But we've tested it, so we're able to basically record voltages and things from the individual antennas or the rectennas. And so, I don't know how much, probably been long. I have a few more slides. So I hope to come back in a couple of years and be able to give a little bit better report in terms of, all right, what's the story on the real solar power beaming thing? There's the brochure, but what's the real behavior of it? And is this something that's viable that we think we can expand? So check back in a couple of years, or I will. But there's more than just sort of these Earth applications. And actually some of the more compelling ones that we're working on now involve other missions, specifically lunar missions. Because one of the hardest things about lunar missions is that they have to survive the lunar night. The lunar night is 15 days of minus 200 degrees Fahrenheit temperatures, and electronics and batteries and everything that's well below their survival temperature. So they die. And so most of the missions that you see have a 14-day. They land right at the start, and they have a 2-week mission period, and then the systems never come back alive after that. Unless they're there are some locations that get sun, and they don't quite have the full 15 days. Those are more on the poles and things like that. But if we really want to start exploring the moon, we need a way to, if we're going to have a robotic lander, say, how can we keep the system alive even, or even thrive during the lunar night? And so this is where this power beaming can really be useful. So think about having some satellites that are orbiting in a lunar orbit, like a low lunar orbit, and they're beaming power down to a lander or a station that's maybe in shadow. The orbiting spacecraft is not, so it's generating power and it's able to beam it down to the lander that maybe is in full shadow. And so we've looked at this. Also, this is part of our research studies in terms of figuring out, well, how many satellites might you need? Because as you saw in that earlier animation, you're not stationary, especially if you're low enough, you're not stationary over a target. So what you're relying on are multiple things passing over all the time and beaming you, hopefully, continuous power. And so these were just some simulations that were run on an earlier research effort where we had admittedly an arbitrary number of 6 kilowatts. Like, what would it take to generate a continuous 6 kilowatt power need on the lunar surface? And how many satellites would you need? And what kind of transmitter would you need on the orbiting spacecraft in lunar orbit? And so you can see the numbers are pretty high. If you just have a single satellite, you need a 250 kilowatt transmitter, which is a very it's a very powerful transmitter. It's probably more than what you could actually manage. But if you have 10 of them, so if you have them in some sort of orbit, spread out, say these are 10 different orbits or 5 different orbits, however many you want, and they can be these low orbits or they can be these very eccentric orbits. The nice thing about the eccentric orbits is that they stay in view longer for certain parts of the moon during its orbit, without getting into details. The bonus is, this is logical, that if you have more satellites, then the transmitter power that you need per satellite goes down quite a bit. And so you're leveraging the larger number of satellites, and the total access time also goes up. The more satellites you have, the more power can be transmitted to your lunar base or your lander. And so the other thing, the final thing that I think also has a lot of value that we're pursuing is satellite servicing. So currently, right now, one of the main limiting factors to most spacecraft is their battery lifetime. A lot of spacecraft just expire because they lose cells and they have a certain lifetime on them. And especially for these high altitude geo satellites that we were talking about, if we can improve and extend their lifetime, that would have a lot of benefits. Fewer launches, the providers could operate their spacecraft longer, so there wouldn't be as much interruption in surface. There's an appeal to them, of course, because they're getting more value for each spacecraft. And there would also be a reduction in orbital debris, like the fewer satellites. If they're burning through them less quickly, there's fewer they have to throw up into these graveyard orbits, at least for now. And so a couple of different architectures you could think about. You could envision a satellite, an SPS system, these space power systems, that could actually beam power to an orbiting satellite, so that a satellite conceivably wouldn't need batteries at all. That's a harder scenario to manage just because of the relative dynamics. What's more interesting is possibly using some of these systems and looking at a new architecture that involves modular solar panels. So you can envision here a spacecraft here that has solar power modules that you could add and expand to be very similar to what we were talking about with the large space structures, but you could add as many as you needed. If they fail, you can replace them. So ideally, you could keep a spacecraft running indefinitely, and they would never have to worry about their batteries running out, especially if you embedded both the power storage and power generation in each of these modular components. And so this is something that Dario, who's sitting right here to my right, he's working on for his PhD research. We're looking at different ways to assemble these structures, how we go about deploying them. There's one thing to stack them all together really efficiently. It's another thing to actually deploy them into large panels. See, these are just some of the concepts. Is definitely not exclusive in terms of how you would start with a stack of these solar power modules and distribute them out and make, in this case, this is just one panel, taking one from the top of the stack, and extending it to the end there. And let's say, for example, a panel were to fail, these systems may be able to repair themselves, have a replacement on board that they can just fix themselves, make them a little bit more resilient. And this just is one concept that we could use where these individual power modules can reorient themselves and repair and replace. Okay, so this is my last slide. I wanted to mainly just highlight and showcase how some of these space-based solar power and SPS systems can offer some pretty compelling options when you start looking at Earth and space applications. There's still a lot of technical and engineering challenges that exist. Still a lot of work that needs to get done to make sure that these can be really viable and that they really are a benefit. But these initiatives like Spider and hopefully Webs, which we'll contribute to, are going to really help get us some real data in terms of how they work on orbit. And so, yeah, we're really looking forward to being a part of all that. So that's all that I have. Thank you very much. And if you have more questions, reach out, please.
Very good. Thank you. Yeah. Any questions?
I don't have a question, but I do have a comment. Brian, you know that we have the Initiative Leads program in Brook Byers Institute. You may have seen it. So there's an invitation always kind of standing out. If you have ideas that would be community building, bringing more people into either the work that you do, or for example, you said, you know, you're doing monitoring, climate monitoring. At the beginning, you mentioned other work that you do. So, you know, SCI, RBI, and Brook Byers Institute are going to a model where they're seeding these initiative leads with the idea that some people at the mid career levels are stepping up and bringing people together in new ways to go for new and interesting programs. And there's an invitation to, you know, every fellow to definitely be thinking about such things. So just wanted to put a bug in your ear on that because we'll probably be running these programs again next year. All right, thank you.
Well, to Beryl's point, I was thinking of, there's a couple things I was thinking about in terms of, well, I wanted to ask if you've started to connect with other people. Anything but a geosynchronous orbit. So you're moving these powered systems around the globe, essentially, and they're crossing over different countries with different, some are friendly, some are not so friendly. What would happen in those cases? You continue generating power where?
Well, you can turn them on and off, so you don't have to transmit, and there may be nations.
But then your cost per kilowatt goes a lot
Possibly.
higher, right?
So there's a lot of interesting concepts when you start thinking about what you could do. These type of systems could potentially access very remote regions, like in the oceans, or maybe in remote parts of land that don't have powered, landlines. So there's that opportunity. You could also say, well, when I'm not transmitting, I'm storing them. So you could have potentially some battery storage that then you wait, you build up, and then maybe you can now transmit at a little bit higher rate if you selectively turn on and off these systems. So there may be all kinds of very clever uses of having something in lower. So it's not always a good thing to have it at this really high stationary point, because then you're only beaming down to a single location. There may be some real benefits to having them low and covering the whole globe because you get more access. But there are some challenges, right? There's some geopolitical concerns. Maybe you don't want them beaming over cities, or maybe you don't want them doing all this. But I think those are solvable problems because the satellite should ideally know where it is very precisely, and you can turn that thing on and off, or redirect it, beam it somewhere else if it's a concern. So I think that's solvable.
The second question was around deployment, and I tend to think of these things as sort of flowers opening up and blossoming. I mean, is there a biomimicry angle here?
There can be. It comes down to how efficiently can you stow them. What's the most efficient, mass to orbit type structures that deploys them most efficiently, and that sort of thing. So anything that would make that more cost effective, mass effective, would be in demand. And we've looked at that kind of stuff. those tend to have to be like very thin film stuff. Sometimes it's difficult to deploy very complex things that are folded more than once. It's very difficult to deploy mechanically. Things go wrong, and they get like, look at like James Webb and all these. They had to spend a decade. It worked, but they spent a decade and $1 billion to make sure it works. It's harder to do with these smaller systems. So.
And I know there's someone on campus, I forget who it is, but I mean, I think they study these folded structures, these origami type like things.
And we've experimented with those types of things, but those things have to be very thin film. And at the moment, these modules that we have they're like that thick, so not very stackable or not very foldable. So. But I do really like the idea about doing a little bit. I wish we had, so if you have somebody who's interested, maybe from a business economics perspective, that could weigh in and wants to evaluate some of the cost benefits, some of the actual.
I mean, that was immediately, I think
costs, that would be great.
Your penultimate slide, is like, this is sort of compelling. And I'm an economist, but it's like compelling to what, compared to what, like what's the kind of, what's the benchmark? And I think it'd be useful to think about what the big frictions have been, right? There's actual launch there, right? Sort of payload launch, there's sort of collection, there's distribution, this, I don't know this space, right? So there's a very high level. I feel like those are the three major components. Where's the greatest loss, right? Efficiency sort of loss, and where has that sort of delta been diminishing the most? Like, I'm sort of curious to see where there's the greatest traction in this potential technology so that one can begin to extrapolate out to some point, T star, this is when it becomes viable. Just like, I always have like the photovoltaics graph in my mind, right? Like just sort of that sort of drop, and you could then extrapolate a little bit. And so in your, not in your mind, but your sense, where is the largest, where are the largest improvements going to come to make this type of technology more compelling or more viable compared to terrestrial solar?
Yeah, I would offhand, I would think it's in that efficiency conversions between the solar to RF to DC.
Okay.
You're losing lots of efficiencies there. If they can improve on that, that would be better. And
so not distribution then, right?
A little bit. I mean, all these launches are expensive and polluting, and they have all these resources that are required to get them up into space. So if we could have a cleaner launch, if we didn't have.
I actually meant energy distribution, right? Because if it is just really cumbersome to bring it down to earth, then you go air to air, right? Then it seems like maybe the most compelling application here is to power other assets that are in space. But I would constantly think about
that's tricky because things are moving so fast in space relative to each other that it's very hard to lock that on.
Okay. Hence the stationary aspect being a bit more.
Yeah, definitely not a solved problem, and I didn't want to say that it was, but compelling is worth a continued look. I would say so.
Where do you get your funding for this?
For now, like the UMP work is sponsored through DoD and AFRL. But that's actually managed by an AFRL program for the nanosatellite program. The rest of the stuff is at the moment sponsored internally. So like Dario is on a 1-year fellowship that's internal to aerospace engineering. And so we're hoping to get more, of course, but I think if we could apply to, I think NASA or DoD would be sort of the natural funders for that, because
Did you say DoD or
DoD, Department of Defense, they would be interested in beaming power directly to maybe some submarine that's way out in the middle of nowhere that has no power infrastructure. That would be great if they could pop up and just receive power wherever they are in the world. So there's one of the drivers for that. Or if you have spacecraft that need power, or maybe you have things that are waiting and then they get power and then they activate, there's lots of different schemes and things for that. Different concepts.
It's a long way from sort of you're kind of pushing along the commercial, more civilian applications.
No, military, I think seems, but the military is also going to think about,
they have just different.
Military is going to pay $30 for a gallon of gas, right?
Right. No, so and that's why it's important to sort of anchor into what the outside options are. And so typically, most technology diffusions happen when the lead users have the highest willingness to pay. And so military is going to be that. So
and it may start with that, but then it has dual use, so like a lot of things do, and then it finds another mainstream use. So.
Yeah.
That's how we got cell phones.
That's great. I need to run.
Yeah,
Very good.
great.
Thank you very
Thank you
much.
all.
Yeah, appreciate it. Thank you all for coming as well. Yeah.